Let us discuss about reduced density operators and partial trace. The density operator, which is also called as the density matrix, describes the state of the quantum system. It generalizes the concept of pure state to include mixed states which arise due to classical uncertainty or entanglement with the other systems. See, what is the point here is that the state vectors, which are basically ket vectors, can be used to represent the state of the quantum system. But the state vectors can be used to represent the state only when the state is a pure state. If the quantum system is in a mixed state, in that case state vectors won't be able to represent the system. So therefore, in that case, the density operators play an important role to represent the state of the quantum system in the mixed states. Now, what about these mixed states? So these mixed states are basically occur when we have partial information about the state of the system, or we have lack of information for the state of the system. So therefore, the concept of statistical probability comes into play at that time when we don't have perfect knowledge about the system. That means we lack information. That is basically the classical probability that we have used to do in our previous classes. So therefore, that statistical mixture of states, meaning by we don't know the exact state which the system can be in, so it is a statistical mixture of states with probabilities attached. That means the system can be in one state with this probability and the other state with the other probability. That is known as the statistical mixture of states. So once the system is in this statistical mixture, the system is termed as to be in the mixed state. But when we know the state of the system, that the system is in state, let's say ket psi, then it is termed as that the system is in state, is in a pure state. So therefore, before we talk about the reduced density operator, let us briefly discuss about the density operators. Though we have already discussed in other videos the density operators for the pure and the mixed case. So let us consider a set of states which are represented by ket psi subscript I. So this is a set of states with probabilities pi respectively. I mean corresponding probabilities. Then the density operator is defined as rho, which is the summation of the product of the coefficients pi with the outer product of psi with itself. So these coefficients are basically the probabilities. So that is why the summation leads to 1 and all these probability values are greater than or equal to 0. This is the case of the density operator for a mixed state. Had it been for the pure state, then PIs would have disappeared. Only the outer product would have left. So let us consider a subsystem in Hilbert space H. The system can be entangled or it is not entangled. That will not matter, because even for the if the system is not entangled, even then it leads to mixed state, or even if it can be entangled also. So that is a redundant scenario. Now, in mathematical terms, given an operator rho, how can we say that this actually is a density operator? Therefore, we should test certain properties on this operator to finally say that this density operator is for either a pure state or a mixed state, and even it is a density operator. The first property that we have to check for is the positive semi-definite. So what does it mean? It means that this matrix element type of property, which is the density operator for a quantum system in arbitrary state ket phi, this matrix element has to be greater than or equal to 0. Now let us try to prove this, whether this property how this property holds. Now if you substitute the value of rho here, because the rho is given by the summation of this product probability and the outer product, then we will see that when we substitute the value of rho, we get two inner products. So therefore we get the magnitude squared of the inner product of psi with phi, and of course these probability values will come in the product as coefficient. So since this square is greater than or equal to 0, we also have assumed, we also know this, since these are probabilities, so these will be greater than or equal to 0. So overall sum is always non-negative. So therefore the density operator is a positive semi-definite operator because it satisfies this property. It has to be Hermitian, meaning by that the adjoint of the matrix, adjoint of the density operator is equal to the density operator itself. The trace is unity. For the purity check, we can say that if the uh, density operator squared is equal to the density operator itself, then it's a pure state, and which also means that the trace of the rho square is 1. So let us now look at briefly about the pure state. So consider the state of the system as ket psi, and ket psi will lead to a density operator which is given by the outer product of this ket psi with itself. Now we want to see the relationship between the state vector ket psi and the density operator. That how statistically by looking at certain properties, that what is the, how can we find, how can we establish the equivalence of the state vector with the density operator. That we say that the state vector can be used to represent the system and the density operator can also be used to represent the system. So let us try to uh, see the equivalence between the two, the state vector and the density operator. Let us consider an observable M and we try to find out the expectation value of this M. In terms of the density operator, the expectation value is given by the trace of this observable A multiplied by the density operator. Right, this is in terms of the density operator. Now you replace this density operator with the outer product of psi with itself. So by using the trace property, we can say that the expectation value comes out to be this matrix element type of item, which is the bra psi m ket psi. And if you remember, this is the expectation value of this observable m if when we are representing the system using state vectors. So we started from the representation of the expectation value using the density operators, and this comes out to be exactly the same as the expectation value if we do it using the state vectors. So therefore there is definitely an equivalence between the state vectors and the density operators, and both can be used to represent the system. But density operators are helpful when the state of the system is in mixed state. Now let us consider an example where we consider a mixed state case, that the 50% chance of ket 0, that there is a 50% chance of quantum state to be in ket 0 and 50% chance of the quantum state to be in ket 1. So we can find out the density operator from here using the density operator formula, and when we express this in the matrix form, so we get this matrix. Now let us try to test this matrix with certain characteristics. Let us try to look for the rho square. So we find out that rho square is not equal to rho mixed. So therefore definitely this density matrix is a case for mixed state. And when we try to look at the trace of the square of the density operator, it is coming out to be less than 1. So again it is a case for mixed state. Had it been for a pure state, the trace should have come out to be equal to 1 for the rho square. Now let us look at what is the reduced density operator. Now let us consider two subsystems, subsystem A and subsystem B. Rho A is the density operator for subsystem A, rho B is the density operator for subsystem B. So if we consider jointly the subsystem A and subsystem B, rho AB is the joint density operator or the composite for the composite system. If we consider jointly, this is this subsystem A and subsystem B, but individually subsystem is having rho A as the density operator, and this subsystem B has rho B as the density operator individually. Now, what is the problem at hand and what is reduced density operator? We are given with this full density operator rho AB, and we want to find out the density operator for for subsystem A or for B. This is rho A and B. So that means we want to find out rho A from rho AB or rho B from rho AB. So that's the problem at hand, and these rho A and rho B are termed as the reduced density operators. This is the full density operator. Now the composite system AB is, so it can be entangled or not, that does not matter, as I have already explained. So let us try to look at, so this is the formula for finding out the reduced density operator for subsystem A, which is given by the trace of trace over B, and you apply this you apply this trace over B on the joint density operator, right? So rho A and rho B are called as the reduced density operators. Reduced density operators can be obtained by using the method of reduction, which is implemented using partial trace. We will see how analytically or mathematically we can obtain this reduction method and the partial trace, and we will also finally look with a numerical example also. What does this mean? This formula actually means that this traces this once we are trying to find out the reduced density operator using the method of reduction, what it does is it traces out, or that means it discards the degree of freedom of system B, and it keeps only the characteristics of the subsystem A. So let us try to define the dimensions of the subsystem A and subsystem B also. Here DA and DB are the dimensions of subsystem A and B respectively, and DA into DB cross DA into DB are the this is the size of the matrix, the joint density operator, right? So what is the method of reduction? First of all, to start with, we will choose an orthonormal basis for subsystem B, and we choose this set of ket J's as the orthonormal basis for subsystem B over Hilbert space HB. So this orthonormal basis will satisfy this characteristics that the inner product of the elements of this set will be equal to the Kronecker delta Jk. So if J is equal to K, in that case this delta is 1. So that shows that this is the case of normalized state, and when J is not equal to K, this delta will be equal to 0. That shows the orthogonality of the elements of the orthonormal basis. And we also say that the summation over all J's and of this outer product of this eigenstate is the identity matrix, will lead to the identity matrix for subsystem. The size of the identity matrix will be the size of the subsystem B. Now this is the overall formula for finding out the reduced density operator using the partial trace method. Now I will explain this. First of all, rho AB, this is the joint density operator of the composite system AB. Now if you look at this formula, you will find that there are terms like IA and IA. This IA is the identity matrix that we do not want to touch the A part in the joint density operator. That means by using this identity at these places, the part that represents the subsystem A will not be touched, and while we do something on the B part, in this in this part we are doing the bra over the subsystem B, and in this case we are taking the ket of the orthonormal basis, and we will do this cron operation from the right and from the left on this joint density operator. Now, so IA cron bra JB is the identity operator. Bra J is a bra that acts on system B. So therefore IA cron bra J acts on full Hilbert space by leaving A alone and applying J to the B part. So that's exactly the meaning I was just trying to explain. This is basically, what does it mean? Think of it as measuring subsystem B in the state J, right? We are measuring B, but we are not touching A. So that is exactly the meaning of this overall formula that we are trying to do. So let us, so this I have already explained. So finally we have to sum over all the of all the cases that will come, and we will sum it over all the eigenstates of subsystem B, right? Sum over all basis states of B. So you perform this projection of each basis vector G of B and then sum the result. So you will get one matrix part for no, you will get the reduced overall reduced density matrix for subsystem A, right? Because you have already, the summing is basically done for all the eigenstates. So once you do the summation, you will get the final reduced density matrix. Now let us take an numerical example, and we consider a well state ket 0 0 plus ket 1 1 divided by under root 2. Let's find out the joint density operator from here by taking the outer product like this. This is the explicit form of the joint density operator, and we finally get this matrix. Right. The computational bases are ket 0 0, ket 0 1, ket 1 0, and ket 1 1. So we will consider the we are considering the computational basis for the orthonormal basis of subsystem B. That means we are considering ket 0 and ket 1 as the two eigenstates for subsystem B. So let us now compute for when ket J is equal to ket 0. So ket J can be ket 0 also and ket 1 also. So there will be two matrices which will be calculated. So one is for ket 0, the other is for ket 1. Now let us first find out for ket 0, and we represent this calculation using M0, and this will be calculated by replacing J with either bra 0 and ket 0, right? In place of J we are putting 0 here because we are calculating for the first eigenstate, which is ket 0 case. Now so let us try to find out the first item here, which is the identity cron bra 0. So this is the overall joint density operator. These are the representations you must understand. So these are the row indices and these are the column indices A, B and A dash, B dash. So row index, which is the bra state, which is given by AB. The column index, which is the ket state, is given by A dash, B dash, right? Which is the column index basically, because the bra represents the row and the ket represents the column. So each matrix element is given by row AB, A dash, B dash, right? And A dash for subsystem A, B dash for subsystem B. These are the indices. So let's now calculate M0 for the case when we are considering ket J equal to ket 0, right? In that case, our so we will consider, so our element will be for ket 0, our matrix element will be P A comma 0 and P A comma 0, A dash comma 0, because we are calculating for eigenstate of ket 0. That means the state B, that means the subsystem B indices will be equal to 0. So that means B and B dash will be equal to 0. So therefore our matrix element will be row A comma 0 and A dash comma 0. So in this matrix, in this overall joint matrix, what you do is you find out the rows and columns for which B and B dash are zeros. So that means this will go, let me put it, this element, this row will go and this row will go, and in the column cases we have to put B dash equal to 0. So this will go and this will go. So of course let me just this 1 by 2 will come here. I am missing 1 by 2 here, so this will be 1 by 2, right? So if you keep these rows and columns, you will get it equal to m0. So that is what our reduced density of matrix, reduced density operator for subsystem state ket 0. This is the so therefore this is the partial matrix that we will get, which is equal to m0 for one eigenstate. So similarly, we can go for the next for the other eigenstate of subsystem B, which is ket1. So therefore, we want to calculate ket m1. In place of ket j, we will put ket1, and in place of row j, we will put row 1. So meaning by B and B dash are both ones. In that case, the matrix element will be row A comma 1 and A dash comma 1. So you apply this these indices on this overall matrix, then you will find out the reduced matrix that will come out to be 0 0 0 half. And so you get two submatrices m0 and m1. So what is the final reduced density operator? This will be the summation of m0 plus m1, and which will come out to be this matrix. So this is the reduced density matrix of A. This is the method of reduction using partial trace to find out the reduced density matrix. Now in this lecture, I will also cover what is a maximally mixed state. A maximally mixed state is a quantum state that represents complete uncertainty. The maximum entropy present in the state of the quantum system will lead to the maximally mixed state over all possible outcomes. Now for a system with Hilbert space of dimension d, let's say the system has a dimension of d, the maximally mixed state is represented by the density operator rho max. Max in the subscript represents the maximally mixed state. So this is given by 1 over d into the identity matrix of dimension d. That is, every basis state has equal probability. So therefore, every basis state has got equal probability. In this case, the trace will be equal to 1. If you try to calculate the trace of this rho max, it will come out to be 1. It is Hermitian. It is positive semi-definite. All eigenvalues are non-negative. Now, this is one of the characteristic of the positive semi-definite property, that it will lead to all eigenvalues which are non-negative. So this is one of the ways we can say that the particular operator is a positive semi-definite operator, if you can say that, if you can prove that all the eigenvalues are non-negative. Now purity, we will try to find out the trace of rho square max, which will come out to be 1 over d. This is minimum purity. 1 over d is the minimum purity, right? And if you try to find out the von Neumann entropy, which is given by minus trace rho max, and if you use this formula, I have already solved it here, you will find that the von Neumann entropy for the maximally mixed state density operator will come out to be log of d, where d is the dimension of the matrix which is representing the density operator. So this is a maximally mixed state where the maximum randomness or the entropy levels are present, and we can we can find out certain properties also for the maximally mixed state. Thank you very much.